Alright, so in this video we're going to take it one step further. We're going to use these equations of motion that we had, or the equation of motion, I should say, as well as the different forces that we've detailed in a previous video. And we're going to start to try to develop some practical understanding of vehicles. So based on our discussion so far, we understand that vehicles should be able to overcome the rolling resistance, aerodynamic drag, force of gravity if there's an uphill situation, internal losses due to friction of motion, and so on. As well as one thing we haven't touched on but is fairly obvious is the vehicle itself should offer a reasonable acceleration and top speed. Now, that means if your vehicle is capable of overcoming rolling resistance and all the resistive forces, let's say, it's not sufficient. So it should be able to also accelerate at a certain rate, and it should be able to reach a maximum speed. You can kind of think about, how useful would it be if you had a car and it wasn't a very fast car, it took you a very long time to get to where you wanted to get to. It wouldn't be a very useful car. You would want it to have some standard or some reasonable capabilities, let's say. So in the United States, they have what they call the U.S. Partnership for a New Generation of Vehicles. So they have this thing, let's call it USPNGV, and I'm sure Asian countries and Europeans have their own type of standard as well. But this is for the United States, and I guess Canada doesn't really manufacture or doesn't have any automotive manufacturers of their own, at least not that I know of. And so that means we don't really have our own thing. Anyhow, there are these requirements, and so there's a requirement on the acceleration, and there's a requirement on the maximum speed. So maybe we can write max speed here. So max speed is sometimes referred to as top speed. In any case, you have basically that you need to be able to go from 0 to 96 kilometers an hour in, let's say, 12 seconds. You should be able to go from 64 to 96 kilometers an hour in 5.3 seconds, and then you should be able to go from 0 to 136 kilometers an hour in 23.4. Sorry about that. That was 23.4 seconds. And the max speed is that you should be able to achieve a speed of 136 kilometers an hour on level road. So that's a grade of 0. And you should be able to reach a speed of 88 kilometers an hour on 6.5% grade. And if you recall, the grade simply means, or a grade of 6.5 simply means that you go up 6.5 meters for every 100 meters that you traveled. And if you're not familiar with the concept of the grade or grade resistance, then you should take a look at the forces acting on forces acting on vehicles video. Forces acting on vehicles video. I'll link that in the description below if you're not familiar with that one. So you'll have a better understanding of what's going on. So now we can move on to our actual modeling. This is a bit of a background type of thing, so we can move on to our modeling. So the equation of motion. The equation of motion, what does that tell us? The equation of motion tells us, Newton's second law that is, tells us, or modified, I guess we had some modified Newton's law, is as follows. And FR is the road load that we called it. So if you recall, this is the road load, is what we said. And this consists of FR, which is equal to mg cos alpha, C0 plus C1 v squared. It's equal it consists of FR. It consists of all three. It's the sum of these three, right? And we've defined this already. So this is FD, which is the aerodynamic drag, which is 1/2 rho AF CD, and we'll say V squared because we're assuming there's no wind. And then you have FG, which is plus or minus. Remember, this is plus or minus depending on whether the vehicle is going uphill or downhill. And we'll assume for this example, or this exercise that we're kind of doing here, we'll assume that it's uphill motion. So we can say uphill motion. Let's start with that. So uphill motion. We can simplify this, or I don't know, I guess it's not simplifying, it's actually expanding the equation by substituting all three of these equations here into Fr, and then we can isolate it for the force, so we can get an expression for the force. So we can get Ft is equal to me dv by dt plus mg c0 cos alpha plus sine alpha plus mg c1 cos alpha plus 1/2 rho af cd, and this is v squared. Now, looking at this equation, there's something that you'll notice, it's fairly obvious. So Ft, we can call it the force equation. So this term is obviously proportional to the acceleration. Obviously, the term is there. You'll see that this term is speed independent, and you'll see that this term, well, I guess it's the whole term, but the whole thing is speed dependent, right? So there's the squared velocity that exists in that term. So that is something to be sort of mindful of. Now, we also know from physics that Pt, or the tractive power, is equal to Ft times the velocity. So if you take the force and you multiply it by the velocity, you'll get the tractive power. And now that's the power basically that that is required in order to exert this force. So there has to be some power that produces this force, right? So you would have some energy. The energy, obviously, there's a relationship between the energy and the power and the force. So we're kind of illustrating that concept here. So the power equation would say then me times v times dv by dt, and you would have mg c0 cos alpha plus sine alpha times v, and then obviously this term becomes v cubed, right? So you have c0 cos alpha plus 1/2 rho af cd v cubed, right? So now you have this equation for your tractive power, and now this is if you have, for a given force, like, so for example, let's say you need to exert a certain force in order to overcome some resistive, or some set of resistive forces, you would need to supply a certain power, or your motor would need to be, or your engine would need to be able to supply a certain power. Now, there are some things that are obvious about this if you look at this. The first thing is that this whole thing is now speed dependent. Well, not even just this, everything is speed dependent. But these two terms are speed dependent. This term was already, even in this case, was kind of already speed dependent because it's the change of the speed, right? But now this is also speed dependent. But I'll put this here separately because one of them was not, and now both are. So there's some things that we can observe here. For instance, at low speeds and on level roads meaning alpha is 0. So we can, let's make some notes, I guess. So let's say low speed and alpha equals 0, right? Majority of the tractive force should be dedicated to the acceleration of the vehicle. Now, why is that? If the speed is low, then these terms are not very large, right? And you see that in the first equation, if the speed is low, this term is really the only one that we care about, right? Because the speed will be changing. This term, if alpha is 0, this term is basically, it's a constant, and this term is basically you don't care about. And in this equation here, if there's a low speed, this term is small, and this term is small, and this term is also small. So all of this stuff is small, and so the acceleration is the primary focus. So low speed and alpha is 0. Let's say focus on dv dt. So you want to dedicate more power to the acceleration. Now, if you have uphill motion, part of the available force should be used to counteract the speed independent term, right? So in this case, remember, this is the alpha term here is essentially accounting for the grade. And if you don't have a grade, then this term obviously it kind of simplifies, I guess is the word I'm looking for, into mgc0, because this term goes away, this term turns to 1, and c0 is usually a small number, so this whole thing will be fairly small. But if it's not, then what you have is you'll actually have to account for this component. But let's consider the case for level for now. But you should be mindful of that, so that if there's uphill motion, part of the available force should be used to counteract the speed-independent term. Since this term, sine alpha, this term is going to be larger than the C0 cos alpha term. So regardless of the grade, there's another thing to observe. I guess we should look at the equations if we're going to do that. Regardless of the grade, for a given tractive force, it is more difficult to accelerate as you get faster. And this is probably something you'll have realized if you're ever driving. If you're driving on a highway or something, and you're driving at like 100 kilometers an hour, it's harder to get from 100 to 120 or 120 to 140 than it is to get from 0 to 20. Right, so that initial 20 is usually easier, and it's from 20 to 40, and 40 to 60 is usually really easy. But it's like the higher you go, the harder it gets, and this is due to the higher fraction of the tractive force that needs to balance the speed-dependent parts. Right, so the tractive force here, as v increases, so as this velocity increases, this term becomes larger. And so you need a larger force then to basically balance the entire equation. So the speed-dependent and the speed-independent components, you need a larger amount of force. It's predominantly the speed-dependent component, because as you get faster, this becomes larger, meaning you need more force to go even faster. So that's the idea there. What else can we look at? So let's look at then in the power equation. You have this factor V. That means you basically need a significantly larger power to accelerate at higher speeds than at lower speeds. That's also another indication of that, I guess, which is what we also established based on this term here. So these two terms tell us that you need a lot more power. Well, for one thing let's take it one step back. This term tells us you need a large force. How do you produce a large force? You need a large power. So these two terms kind of shed light on that notion. And so what you have is the way we actually I guess use, or the best way to implement or to meet these requirements, I should say, is to use what they call the two region. So it's called the two region. Sometimes it's called the torque speed. So let's call it torque speed. But because torque can be related to force, they'll call it force speed, sometimes characteristic. And that's the main objective of this, or the main concept, I guess, that we wanted to arrive at in this video, is this torque speed characteristic. So the idea is this. We're now going to have two regions where we're going to operate, because in one case you see that we need power, in one case you see that we need force. So we can have one region where we have constant power and one region where we have constant force, and then we can kind of adjust. And I'll illustrate the concept in a second. But the idea is that the power plant will offer a constant force up to a certain speed, and we call that speed the base speed. And then what will happen is the force will decrease inversely to the speed after that, well, the speed of the vehicle after the base speed. Now, it sounds a little complicated, but it's not very complicated, and you'll see a graph, or I'll show you a sort of characteristic curve type thing, and that'll shed some light on that. Now, the importance of this is that in electric vehicles, this impacts the size of the motor, the converters, the batteries, and all that kind of stuff. So it's very important that we pay attention to this stuff. So what does this thing actually look like that I just spent so much time describing, but not enough time actually showing you? So let's take a look at this curve. So we have a curve, let's say, that looks something like this. Well, that's just a set of axes. It's not really a curve. But what we're going to do is we're going to consider the fact that, let's say this, okay? So this is going to be our speed. Now, this speed can be an angular velocity, or it can be a linear velocity. Linear velocity? Is that the word for it? I'm going to say linear velocity, or a straight velocity. And here what we're going to have force. Well, I should probably stay consistent the way I did it there. So we're going to have torque, or force, slash power. Okay? And that may look like it's a function of, but it's not a function of. So I'll draw two different, I'll draw the labels here. In any case, what you have is the power is going to do something like this. It's going to go from 0, and it's going to go up to some maximum here. So you're going to have some power. It's going to go, you're going to increase the power, and then you're going to go constant after here. And while that's happening, or at the same time, I guess simultaneously, you're going to have your force, or your torque, constant there, and then you're going to decrease that inversely to the speed of the vehicle. And that'll decay with a 1 over v or a 1 over omega dependency. So this is the power, and this is the force slash torque, depending on which way you're doing it. Because the thing is, the two are proportional to each other, just with the difference of the units, basically, and you can relate them to one another very simply. Another thing we should probably mention is that this thing is a 1 over omega or a 1 over v dependency. That's how it decreases. So we label these regions as this is the constant torque or force region. Seems logical enough. This is the constant power region, which is what you would probably expect. Constant power region. And this thing here is the base speed that we discussed previously, and it'll be called omega b, or we call it vb, depending on which type of velocity we're dealing with. Now, here we have tt max, and we have this power here is pt max. So that's the tractive torque and the tractive power maximum. And I guess the last thing we can kind of just talk about here is that pt max is equal to tt max omega b, which I guess is the same thing as saying ft max times vb. So what does this mean? This is showing us exactly that. This is the profile that basically every vehicle operates under, and what it does is it allows us to better utilize the power that we have available to us, and we'll see this in an example in an upcoming video, where we'll actually look at two different ways of utilizing the engine, or the motor, whatever you want to call it, the propulsion. There's two different ways of approaching the propulsion, and we'll approach it first just the standard way, and then in the second part we'll look at it using this type of profile, and you'll see that this is actually a much more effective way of approaching propulsion. So what you have again is, during this time, you can say that, let's say from 0, because this is exactly 0, 0 point here. That's not really a good way of doing it. This is 0 here. So from 0, when your car or your vehicle is at steady state, and maybe we should use a different color entirely. Why don't we use this? So you start from 0, and as you start to speed up, or initially when you're at rest, you apply the maximum torque, right? So that's what you're doing here. This is the maximum torque. Now, as your vehicle starts to speed up, you go to some base speed, and this base speed is usually a provided, rated type of value. And so as you go do that, the amount of power that you're generating, or that you're using, increases. Once you get to the maximum power of the motor or the engine, you start to decrease the speed, or sorry, the torque, I should say, and the speed increases. You decrease this, and you keep the power constant. And that's the idea here. And again, we'll look at how this applies to a real example, and the actual difference that this can make in providing a more effective and efficient utilization of the overall system. So what did we do here? It was a relatively straightforward thing. I guess we spent a lot of time explaining the equations, which is always useful. But I guess we start from here with the equation of motion, and adding all of its constituent components, which are basically the resistive forces, which are these. And then you can kind of isolate them for speed dependent and independent. And you can think about things like, where are certain terms dominant? So we realize that at low speeds, this term is obviously not dominant, because this term is v here is very small, and so that this term would be dominant, and that means that at low speeds most of the force should be applied to try to speed the vehicle up. Then as you get to higher speeds, you don't need as much of force, because for instance, in this case, if you want to maintain this balance, if if v becomes large, then ft can become smaller, and they can change proportionally, which is exactly what happens here, right? So as v is increasing, you're decreasing the force because you want to keep power constant at that value, which is exactly what this equation is telling us here, which is a concept of physics. This is not unique to electric vehicles, or any vehicle, that is. This is a concept of physics. So, that being said, I hope this was helpful. If you have any questions, feel free to leave them in the comments below. Like and subscribe to support the channel, and we'll see you in the next one.